Hello and welcome to Lecture 17. I'm Chris Mack, a professor for the class From Data to Decisions. This is the first of a series of lectures where we're going to talk about outliers, an important topic that is often misunderstood and often misapplied when working with real data. So let's begin by discussing what an outlier is. There's lots of different definitions that people use for outliers, and sometimes I think the definitions where people get the concept of outliers wrong. Some people will say the definition of an outlier is an observation that is different from the others. Well, that's not really good enough. Really what we mean by an outlier is we observe something, measure something that is so different than what we expected that we suspect that a different mechanism was at work in creating that data point. It is an error, potentially, but a systematic error. We don't want to think of outliers as being just occasional, rare, or random events, but rather something went wrong, and that's what caused the outlier. So our assumption typically is that outliers are large, one-time, systematic errors. And we need to deal with them differently because we often do our analysis assuming we only have random variations, random errors. And if this large systematic error were included in the data set, it would screw things up. We'll come back to that in a little bit, but this name outlier, which I'll use that term mostly, is also called a data flyer, wild observation, sometimes a maverick data point. Maverick meaning that maybe it's not necessarily bad, but just behaving badly. There are a lot of possible causes for outliers, and as we'll discover as we study outliers in more depth, sometimes figuring out the cause of the outlier is the most important thing you could do. One possible cause is just an error in recording the measurement. If you're doing things the old-fashioned way and writing down numbers in your lab notebook, maybe you wrote down 48 when the real measurement value was 84. Well, there's nothing about the physics that is important in that particular outlier, simply mistake in recording. But if we're making measurements in a more automated way, there could still be failures in the measurement tool, the measurement process. Things can go wrong, and you get a number that just doesn't make any sense. And in fact, is not reflective of what's really going on in the process. Sometimes you're measuring multiple samples and something went wrong with one of the samples. You forgot to bake it. You forgot to add the reagent. You forgot to process it in the proper way. And so it's different than all the rest. And there can be failures in the experimental process as well. These are all systematic errors, problems that don't occur just because of random chance, but because of something that went wrong. But this cartoon, which is one of my favorite statistics cartoons of all time, really outlines the difficulty we have with an outlier. Here's a bad data point, but why is it bad? Is it bad because my theory is wrong and something is happening that's anomalous, that is different than what you expected in your trend? Or is it just, as I said, a bad data point because the measurement was bad or the recording of it was bad? Does the outlier have something to teach us about the mechanism that we're studying? Or does it not? This is the big question that we face whenever we see an outlier in our data. And it is the difference between an outlier and a spurious data point. As I said, an outlier is an observation that's so different from the others that we suspect it was generated by a different mechanism. A spurious data point, on the other hand, is a data value that has nothing to teach us. We're studying a particular process, a particular mechanism, a particular physical phenomenon. A spurious data point is something that can't teach us anything about what we're trying to learn about. So if we see a spurious data point and we realize that it is in fact spurious, we toss it out. We have no qualms about getting rid of that data point because it doesn't have anything to teach us. But not all outliers are spurious. Sometimes the outlier, the thing that's different, the different mechanism, is a discovery. There have been many famous examples throughout the history of science where a mistake turned into a discovery. And if we simply tossed the data output out and assumed it was spurious, we wouldn't have learned. And famous scientists wouldn't have learned the things they did by treating every unusual measurement as spurious. You can identify something as an outlier without coming to the conclusion that it is spurious. Judgment, your ability to decide one way or the other, is not statistics, it's scientific judgment. What we're going to do in the next few lectures is help us identify what an outlier is. But the judgment as to whether an outlier truly is a spurious data point or not, that's something statistics doesn't tell you. That's something that your scientific judgment must inform you. So why should we detect outliers? Many, many times we use what are called non-robust statistics. If your statistics are not robust, then one bad data point is enough to ruin the analysis. Look at the mean. If I have one data point that's 10,000 times bigger than all the other data points, our calculation of the mean is going to be completely off unless we have hundreds of thousands of data points. If we're doing ordinary least squares regression, one bad data point's enough to violate the normal distribution assumption. So we detect outliers. Often we detect outliers for the purpose of correcting our measurement process or our experimental procedures or something that gave rise to that outlier, adjusting either the process or the data itself, or rejecting the outlier. We're going to talk more about what we do with an outlier in a couple of lectures. We spend the first couple of lectures talking about how to, in fact, detect outliers. But detecting the outliers, in fact, is only the first step. What we'd really like to do is discover the mechanism that caused the outliers, or outlier. As I said, sometimes it's more interesting to discover the cause of the outlier than the rest of the experiment. Not always, but sometimes it is. So whenever we see an outlier, we should take it as an opportunity to discover about something else that's going on. And it could be just a matter of discovering a way of improving our measurement or our experiment. The basic idea of outlier detection is the idea of rare events. We have rare events. We have extreme things that can happen. But those rare events are not really outliers. They're simply rare events that happen naturally. But thanks to statistics, we can calculate the probability that these rare events will happen. And we can compare the probability that a rare event would happen to the probability that data point we actually got might have happened. So here is a table of two-sided p-values assuming a student's t-distribution. So what I've done is talk about this a little bit more. I've taken the data point, I've subtracted off the mean, and then divided all of that by the standard deviation of my sample. We call that studentizing the data. And if the value is 3, that means my data point is 3 sigma away from the mean. If it's 5, that means my data point is 5 sigma away from the mean. But obviously, the further you are away from the mean, assuming that you have a student's t distribution, the more rare it is. It's frequently it happens. But that frequency depends on the degrees of freedom. That is the number of data points. For a student's t distribution, the degrees of freedom is the number of data points minus 2. So if I have 5, that means I have degrees of freedom equal to 5, that means I have 7 data points. Well, the reason that's important is your estimate of the standard deviation is quite poor. You only have a few data points. And so your uncertainty in the estimate of the standard deviation is poor. You also have more uncertainty in the estimate of the mean. So you get more variation in the studentized data point when you have less data points, less degrees of freedom. As a result, what's the probability, the p-value, of getting a data point that's 3 standard deviations away from the mean or larger? Well, if I only have 7 data points, 5 degrees of freedom, then there's about a 3% chance of that happening. But if I have 20 degrees of freedom, there's a 0.7% chance of that happening. So it's gone down, significantly. If I have 102 data points or 100 degrees of freedom, then there's a 0.03% chance of getting that each data point was 3 sigma away. Any given data point might be 3 sigma away. So the number of data points as well as the magnitude of the deviation from the mean determines the p-value. Remember, the p-value is going to be the probability of getting a data point that extreme or more just by random chance. And we're going to use this idea of what's the probability of a rare event in comparison with the actual data point that we got as a way of judging whether we're seeing just a kind of a random rare event or something systematic. So how do we use rareness to detect outliers? We're going to compare the p-value of some extreme data point, the probability that you would get that data point given some assumptions about the underlying distribution, and compare it to 1 over n, where n is the number of data points. If the p-value of a data point is much smaller than 1 over n, we say that data point is an outlier. Another way of thinking about it is if I take the p-value of the most extreme data point that I have in my data set, multiply it by n, the number of data points in my data set, that is the probability of getting 1 data point out of the total n number that is this unusual or more unusual just due to random chance. To do that calculation, it assumes we know the underlying distribution. We have to assume a particular distribution in order to calculate a p-value. Often assume a normal distribution, but we don't have to. We could assume a student's t distribution, probably more accurate for most of what we do. Either way, we assume a distribution to calculate the p-value. Take the p-value, multiply it by n. That's the probability of getting 1 data point out of n this unusual. One very simple way of identifying something as an outlier, that is, we reject the data point as being an outlier, is if the p-value is less than 1 over 2 times n. In other words, the p-value times n is less than a half. The probability of getting 1 data point out of n this unusual is less than a half. We call that Chauvenet's criterion. Of course, this 1/2 is just an arbitrary threshold. We could have picked a tenth or a third or something else if we care to. But this 1/2 value is commonly used and known as Chauvenet's criterion. There are many other statistical tests for detecting outliers. We're going to go through all the ones in this list. None of them are perfect. They all have their faults and difficulties, and we'll try to point them out. In the end, it's going to be tricky to decide whether a data point really deserves to be characterized as an outlier. And then once you tag something as an outlier, what are you going to do with it? All right, so we'll get to that. Let's talk about what is probably the first and most useful way of thinking about outliers, and that is the multiple of IQR test. This is really more of a way of labeling outliers to decide what whether you have any data points that are worth testing. The reason it's good is it uses a robust measure, interquartile range. The interquartile range is the difference between the 75th quartile and the 25th quartile in our data. Quartiles are robust. The 75th quartile is insensitive to the 25% of the data that's larger than it. The 25th quartile is insensitive to how small the smallest data points are, 25% of them. So you can have a lot of bad data points or outliers, and it won't affect your IQR very much. So the interquartile range is a robust measure of the spread in your data that is insensitive to a few outliers, quite a few outliers actually. So define an upper limit. Any data point above the upper limit we can label as an outlier as being the 75th quartile plus 1.5 times the IQR. Now this 1.5 times factor is just an empirical number that we've used that seems to make sense. And the lower limit is the 25th percentile, the 25th percent quartile, minus 1.5 times the IQR. So we define these upper and lower limits. And any data points that exceed them, we label them as outliers. Typically, when we label them, it means we're going to think about them. We're going to study them. We're going to maybe perform some statistical test on them. But if something is not labeled as an outlier, we generally say, oh, no outliers in this data set, and we move on. So this is a great way of identifying those data points that you want to study more. For a normal population with a large value of n, we typically get about 1% of the data points that are labeled in this way, just due to random chance. Well, if you have a lot of data points, that means if you have more than 100 data points, you're going to expect to see some data labeled as outliers by this method, maybe more than you'd like to pay attention to. So sometimes we define a far outlier by using a 3 times IQR criterion. So instead of multiplying the IQR by 1.5, multiply by 3, and we call those far outliers. And for large data sets, we may decide that only the far outliers are things we're going to pay attention to. An easy way to display these outliers is in a box and whisker plot. Hopefully you're all familiar with box and whisker plots, where we plot the median, the upper and lower quartiles as a box. Then we put the whiskers on, these lines that end in our maximum and minimum values. Well, the maximum and minimum values assume that we don't have any outliers. If we do have outliers, we label them, remove them, and then plot the max and min values without outliers here and here, and then plot the outliers as separate data points. So those 2 stars means we found 2 outliers that are above the IQR criterion. Well, as I said, that's a method for labeling data points for further testing. What kind of test might you do? Well, one very simple test is called the Dickson Q Test. We find an extreme value, the one that we think is going to be the most likely as an outlier. It's either the maximum or the minimum data point, right? So we take either that maximum or minimum data point, our suspect, and then we see how close it is to its nearest neighbor. So here's that suspect data point. It could be the max, it could be the min. And then we look at the next closest data point in an ordered list of all the data points. The difference between those two we call the gap. So this is the gap between the most extreme data point and its nearest neighbor. We then compare that to the full range of the data. And this ratio we call Q. Then we have a table of critical Q values, which I'll show you in a moment. And we ask, is this Q value more extreme than the critical Q value? If it is, we say we've identified an outlier. I'm saying we're going to reject it as an outlier here. That's just kind of a shorthand notation. By the 3rd lecture in this series, I'll explain to you the different ways that we can treat outliers once we've identified them. But nonetheless, I'll just say reject it now. That doesn't really mean we're going to throw the data point out and never think about it again. We may do that or we may not. But here, saying, well, I will classify it as a failure of the Dickson Q test if the Q value is bigger than the critical Q value from the table. Dickson Q test is not very popular when we have a large number of data points. There are better tests to use. We're going to talk about some of those better tests later. But the Dickson Q test is useful with a small number of data points. Most of our other tests are going to involve calculating a standard deviation of the data. And when you only have a few data points, that standard deviation has a lot of uncertainty to it. The Dickson Q test doesn't involve calculating a standard deviation, so it tends to work a little bit better with really small data sets. It does have a very serious problem, and that problem is masking. If you have two outliers on the same side of the mean or the median, then one of those outliers can mask or hide the other one. Let me show you. Suppose I have data that I'm plotting using the box and Whisker plot that looks like this. All right, we're going to take the gap, the extreme value minus its nearest neighbor, that's the gap distance, and divide by the full range of the data from max to min. Right? So that would give us a Q value, and maybe that Q value is enough to say, yes, we have an outlier here. But what if I had a second data point here in that data set, and it's pretty close to the first most extreme value? In other words, what if I had two outliers, both kind of close to each other? Well, there the gap would be quite small. And the ratio of the gap to the range being small would result in a Q value that says, oh, I can't reject this data point. In other words, the extreme value is being masked by a second outlier. If you only have a few data points, the chances of getting two outliers become kind of small, and so maybe you're not too worried about this happening. Larger data sets, it's more likely that you'll get a masking data point. So we tend not to use Dickson Q tests for large data sets, as I said. But even for small data sets, this masking problem is something we worry about. Here's the Dickson Q test table that I've gotten from a publication where they did some, I believe they did Monte Carlo simulations to generate these values. This particular table assumes that the underlying distribution is normal. If your underlying distribution, the distribution without the outliers, is not normal, then this Q test table is not appropriate. And that's going to be true for, as it turns out, all of the tests that we do. They're all going to assume an underlying distribution which is normal. And so all the work we did to try to decide whether or not it's reasonable to assume the underlying distribution is normal comes into play here. Now, point about the statistical significance. We're going to have to decide on a statistical significance, an alpha level. Alpha is the risk of rejecting a good data point as being an outlier. So we say, this is a bad data point, maybe I'll throw it out. Alpha is the risk of throwing away good data. So what risk are you willing to take? Generally, you want the alpha that you use for outlier rejection to be smaller than the alpha you use for everything else you're going to do in your data analysis. If you're going to do some curve fitting and report the coefficients of your model, confidence intervals around those coefficients, you're going to pick a particular alpha significance level for creating the confidence intervals. If you're going to just report the mean and standard deviation, you'll also report confidence intervals for those statistics. Well, when you do outlier rejection, you want to make sure that you use confidence intervals that have a much more extreme alpha than those for the rest of your data analysis that you do after you've rejected your outliers. So for example, 0.05 confidence intervals for your normal data analysis, an alpha of 0.05. you would want to use something more like alpha 0.01 for purposes of outlier rejection tests. So this is true for the Dickson test. It's true for all of the statistical tests for identifying outliers. We want the alpha value to be smaller by at least a factor of 2, factor of 5, sometimes even a factor of 10 compared to the alpha value we use for the rest of our data analysis. All right, let's look at what we've learned in Lecture 17. As always, you should be able to quickly and easily answer each of these questions. If not, please go back and review the material. What is an outlier? Please provide the definition. What is the difference between an outlier and a spurious data point? How does the box and whisker plot label or identify outliers? And finally, you should be able to perform the Dickson Q test, but also understand what kinds of things can go wrong with this test. Well, we have a lot more to do with outliers, and that will be the subject of our next lecture. Till then.